Good morning, students. I am Dr. A.K.Jaithunbi, Assistant Professor from the Department of Computer Science and Engineering, RMD Engineering College, which is an autonomous institution. Right? So today let us see deterministic finite automata minimization. So you all are familiar with DFA, which is a 5-tuple, right? And also we have studied about NFA and epsilon NFA. Now, as a computer science students, our main aim is optimization. So there are two types of optimization: minimization and maximization. So in our finite automata, when you are going to design an automata for a given regular language, we are supposed to have only minimized states, right? So for a given regular expression, there are more than one finite automata. Okay, so our main intention is to have minimized or reduced number of states. So obviously our view is to eliminate the redundant states. So today let us see about DFA minimization, which is quite an interesting topic. Right. All are familiar with DFA, deterministic finite automata, which is a 5-tuple. Now, Q is the finite set of states, where sigma is the input alphabet, delta is the transition function, Q naught is the starting state, and F is a set of final and accepting states. And you all know that F is a subset of Q, right? Now, what is DFA minimization? Right. So, our optimization is minimization. We are supposed to reduce the number of states. How to reduce the number of states? We are supposed to eliminate the redundant states. That is, duplication should be avoided. There should not be any redundancy. For example, this following DFA accepts the regular expression A or B plus. Now, your plus is a positive closure. So, it means that it is repeated one or more number of times. So what is another closure you are familiar with? It is clean closure, star. If you have A or B clean closure, your clean closure star is 0 or more number of times. Right. Now if you see this diagram, from S0 for the transition B, I am moving to S1. Once again, there is a transition for B to S2. Right. Now you find that S1 is not necessary here. So I can combine the states, right? Let us see how we can combine, how we can eliminate the redundancy. So these two DFAs are equivalent, right? So if I combine S1 and S2 as S1, right? So from S0 in the first DFA, for B there is transition to S1, and for A there is transition to S2. Now if you find, if I want to combine S1 and S2, right? So for from S0, right, which is a starting state, for the transition A and B, it goes to S1. So if you find the state S1 in the first diagram, it is having a self loop for A, and S2 is having the self transition for A and B. Since I'm combining S1 and S2, so I'll be having the self transition for S1 as A comma B. This is very quite interesting, and you should understand, and you should try to combine the states here. Right. So this is a DFA with the three tuple and the input alphabet A comma B. Right. So I'm going to minimize the state by eliminating the redundant state. So I find that S1 and S2 can be combined. So I'm eliminating one state. So I combine S1 S2. I keep only one state as S1. Accordingly, I combine the transition also. Right. Now this is a state minimized or just minimized DFA. So okay, every other remaining state is necessary. Right. Right. The task of DFA minimization then is to automatically transfer a given DFA into a state minimized DFA. Okay, there are several algorithms and variants. For example, you have two methods, basically tree method and your table filling method. Right. So in your tree method, what we'll do is we'll be combining the accepting state and non-accepting state. So we'll be having two groups, G1 and G2. Right. And in each and every state in the group G1 and G2, you will find that a resultant transition states. If it goes to the same state, you will have it as a separate group. If it goes to G2, you will keep it as a separate state. If it goes to G1, G2, it will be in separate group. If it goes to G2, G1, it will be in separate group. And you will repeat this step till there are no more, equivalency. Right? So that is the tree method. So in our DFA minimization, we are supposed to find equivalent state and the distinguishable state. The states which are equivalent, right, they will be combined as one. The distinguishable states will not be combined. right? So let us see that DFA M is equal to Q sigma delta Q naught F. You all are familiar with this. Two states P and Q are distinct. So I said that you have equivalent states and distinguishable states. How you say the two states are distinct? If P in F, that is F is the final state, and I said no, you are supposed to divide the group into accepting and non-accepting state. That is final state and non-final state. So one P will be in final state and Q is not in the final state, right? So or vice versa. For some alpha in sigma, delta of P comma alpha and delta of Q comma alpha are distinct. That is, the resultant state for the transition of P comma Q for the given input string is different. Right. So using this inductive definition, we can calculate which states are distinct and which are equivalent. Right. If the states results in the equivalent states for the given input symbol, we can combine that state and thereby we can reduce the state and we can minimize the DFA. Right. Now create lower triangular table distinct, initially blank. Right. So this is the algorithm, right? So for every pair of states P comma Q, if P is final and Q is not or vice versa, what I'll do is, if it is distinguishable, that is, if it doesn't result in the equivalent states, then I'll mark in the table that respective row and column as epsilon. Now loop until no change for an iteration. For every pair of states P comma Q and each symbol alpha, if distinct P comma Q is blank and distinct delta of P comma alpha, delta of Q comma alpha is not blank, then we say that it is distinct. Combine all states that are not distinct. That is, if you find the resultant states are same, then it will be equivalent and we'll combine those states. Okay. So it's very simple. So we have three states, S0, S1, S2. So I form a triangle, right? So it is like a lower triangular matrix, right? In the x-axis you have S0, S1, S2, right? In the y-axis you have S0, S1, S2. And it is, we are going to fill the lower triangular matrix that is below the diagonal elements. Okay, right? Other elements will be left empty. Right, so if you find for S0, S1 and S2, it is distinct. So we mark it as epsilon. Now S0 and S1 is different, S0 and S2 are different. They are distinct. They are called as distinguishable states. Now which are equivalent? S1 and S2 are equivalent. They are not distinguishable. So we leave them as blank. So it means that S1, S2 can be combined. So label pairs with epsilon where one is a final state and other is not. Right. So there is no changes occur in the second iteration also. So you find that distinct S1, S2 is empty. So S1, S2 are equivalent states. Hence we can combine S1 and S2. So we are going to merge S1 and S2. Okay. So this is how we minimize the DFA. Okay, students. So minimizing DFA is very, very important concept. As our optimization is minimization, we are not supposed to have extra or redundant states in our DFA diagram. Okay, so ultimately what will happen is the time consumption will be more to check whether the given string is accepted or not. Okay, students. So that's all about DFA minimization. Thank you, students. Let us see in the next class.